So we'll learn now how to make the layout of a half adder as seen here in the notes. Half adder has two inputs AI and BI and two outputs sum and carry. And internally the half adder is a combination of one XOR gate and one AND gate. The XORing between the inputs AI and BI form the sum output, while ANDing between AI and BI form the carry output. The truth table of a half adder is as shown here. Now the approach is that we are going to convert one multiplexer into an XOR gate. We are going to convert another multiplexer into an AND gate, and by combining these two multiplexer based XOR gate and multiplexer based AND gate, we can actually have the schematic for a half adder. Now we have already learned how to make a transmission gate, verified its functionality. We also learned how to combine two transmission gates to form a multiplexer and also verified its functionality. Now what we do is that we combine the verified layouts of two such multiplexers and convert them into XOR gate and AND gate in the following manner. So we see here that we can consider a multiplexer as a block having three inputs I0, I1 and S and the output Y. So consider AI and BI as the two inputs of the half adder. If in a multiplexer I connect the input BI to the first input I0 of multiplexer and I complement it and apply it to the second input I1 of multiplexer, and I apply the input AI to the select line of multiplexer, then multiplexer will now function as an XOR gate. Similarly, if I take another multiplexer and if I connect the first input I0 of this multiplexer to ground and I apply the input BI to the second input I1 of multiplexer, and like before I connect or apply the input AI to the select line of multiplexer, this multiplexer now starts functioning as an AND gate. Now if I combine these two multiplexers in the following way, then what I get is a half adder. Now the combined schematic, we see here I have placed two multiplexers. Let the left multiplexer be called as mux1 and the right multiplexer be called as mux2. We see here that the inputs AI and BI of half adder are connected in this way. The input BI becomes the I0 input of mux1 and also the I1 input of mux2. Similarly, the input BI is complemented and applied to I1 input of mux1. The select lines of mux1 and mux2 are now connected together using polysilicon layer, and the input AI is applied to it. And the output of first mux forms the sum output, and the output of second mux forms the carry output. Also note that the inverter used to invert or complement the input BI is a CMOS inverter. And we see here that this is the layout ready schematic for a half adder. We can clearly see the left and right sections are identical. Only difference is that the left section is a 2:1 multiplexer converted into XOR gate, and the right side is a 2:1 multiplexer which is converted into an AND gate. Now important things to note are that this is the input BI which is connected to I0 of mux1 and is also connected to I1 of mux2 using a metal 1 layer. The select lines of the two multiplexers are shorted together using polysilicon layer in this way from here to here, and the input AI is given. Similarly, we see that the input I0 of mux1 is connected to ground and everything else remains the same. One more thing is that the input BI is now inverted using a CMOS inverter and the output is connected to input I1. Now, understanding this layout, we can directly move to the tool and start making the layout. Now, because my half adder is a combination of two-stage multiplexers, when I go to the layout, I am going to insert the layouts of two multiplexers, and I am going to convert one mux into an XOR gate, another mux into an AND gate. Over to the tool. Now we are already having the verified layout of two-stage multiplexer, and we are going to insert that layout twice in this way. First we'll save this layout as a half adder, file, insert layout, mux using TG, insert it again, mux using TG. So now please note that this is my mux 1 and this is my mux 2. This is to be converted into XOR gate. This is supposed to be converted into an AND gate. So now what I do is I will rename the outputs. So we will rename the left multiplexer's output as sum, and we will rename the right multiplexer's output as carry, which shows that this multiplexer is to be converted into XOR gate and this mux is to be converted into an AND gate. Now what we do is that we can first and foremost connect the select lines of the individual multiplexers by using polysilicon layer. Take polysilicon layer and we can directly connect it like this, because we can cross metal 1 layers easily without any problem. So we have connected it like this, and we can delete one select line signal, and we can rename this as the input AI of half adder. Now going further, we will rename the input I0 of mux 1 as BI, because it is going to be getting the signal BI. Now we know that the input I1 of mux 1 is supposed to receive the complemented version of BI. So we can also delete that signal here. At the same time, the input I1 of mux 2 is supposed to receive the BI signal, this one. So we can also delete this. Again, we see that the I0 input of mux 2 is supposed to be connected to ground. So I can double click this. I can name it 0, and I can also give it as ground. So the name is 0 and the value is equal to 0. Now what we do is that we have to connect this input BI also here. So what we can do is we can use this and we can connect the signal, route the signal like this from here to here. So we take metal 1 and we connect it like this, and we have it cross over the polysilicon layer and connect it like this. So thus we have connected BI to the input I1 of mux 2. Now what we need to do is that we have to add one CMOS inverter here, which we will do in the following way. We will put some cuts here. We will put the first cut here. We can put the second cut. We will first move the signal here. We can put a cut here. We can put a cut here also, and we can stretch and move this here, and we can make the connections again. Polysilicon, there is some malalignment, so we can put a cut again here. We can stretch and move little bit down. Take polysilicon. Again, there seems to be a malalignment. Now we will construct the inverter. PMOS. And MOS. Metal 1. Apply VDD. Apply ground. Polarize the N-well. And now we can little bit move it slightly, because we need to apply the signal BI as an input to the inverter. So what we can do is we can first flip the inverter horizontally in this way. So we have the gate facing the side. Now we can place a poly to metal 1 contact and put it here. Take polysilicon. We need to little bit move it because there may be a DRC error. Take polysilicon. Take metal 1. So now we have connected the signal BI to the input of inverter. Now we have to give the output of this inverter to the input I1 of mux 1. So we can take this like this, can take it like this, and we can take it like this. Okay, so we will just move the sum output a little bit above so it is visible. So now let us check. The input AI is given to the combined select lines of mux 1 and mux 2. The input BI is given here, BI bar is given here, and the input BI has also been routed to the input I1 of mux 1, and the input I0 has been connected to ground. So we will save this, do a DRC. There is no error. You can just say simulate. We can adjust the frequencies after observing the outputs. It's difficult to appreciate now. What we will do, that we will change the frequencies of AI and BI. So we'll go to AI and we will give it a frequency of, say, 2.5 gigahertz. We'll give the frequency of BI as 5 gigahertz. We will see what is output. Reduce the number of cycles. Output seems to be distorted, so you can reduce the frequencies. Go to AI, make it slower. Go to BI, make it slower. Assign, save, simulate. You can remove all the measurements. Now we can verify if the layout is satisfying the truth table. So 0 plus 0 is sum 0 with a carry 0. 0 plus 1 is sum 1 with a carry 0. 1 plus 0 is sum 1 with a carry 0. And 1 plus 1 is 0 with a carry 1. Hence we see that the layout is giving an output which is satisfying the truth table of a half adder.